You're listening to Scientific Giants Who Changed the World. Each episode stands beside one mind and follows a thread of curiosity until it ties to the world we inhabit. Today, we enter a story that begins with desperation and ends with one of medicine's most profound reversals. A disease that once meant certain death, becoming something a person could live with. This is the story of insulin. And at its center are two young men in a sweltering lab in Toronto, Frederick Banting and Charles Best, trying to steal fire from biology and carry it back to the people who were burning. To understand what insulin meant, you have to understand what diabetes meant before insulin. In the early 20th century, especially for children with what we now call type 1 diabetes, diagnosis was almost a sentence. The body could not regulate blood sugar. Patients wasted away despite eating. They became weak, thirsty, confused. Without treatment, they slipped into coma and died. Doctors could offer only brutal dietary regimens, near-starvation diets designed to keep blood sugar low by keeping food low. It could prolong life briefly, but the price was misery and eventual decline. Families watched their children disappear in slow motion. The medical world knew something important. The pancreas was involved. Experiments had shown that removing the pancreas from animals caused diabetes. Something produced by the pancreas, some internal secretion, seemed essential for controlling sugar. But extracting that substance was the problem. The pancreas is full of digestive enzymes that quickly destroy proteins. Any attempt to grind it up and inject an extract into an animal tended to fail, because the active substance was either destroyed or overwhelmed by toxins. By 1920, this problem had been worked on for decades. People were close, but not close enough. Then Frederick Banting, a young Canadian surgeon with limited research experience and a restless mind, read about the pancreas late at night and had an idea. It was not a polished theory. It was a plan, an improvised assault on a locked door. Banting believed that if you could stop the pancreas from producing its digestive enzymes, if you could disable the parts of the gland that make the enzymes, then the remaining tissue might still produce the mysterious anti-diabetic substance without destroying it. The pancreas contains clusters of endocrine cells called the islets of Langerhans, which secrete hormones directly into the bloodstream. Banting's idea was to tie off or ligate the pancreatic ducts in animals, causing the enzyme-producing tissue to degenerate while leaving the islets more intact. Then he could extract the secretion from the remaining tissue and test it. It was crude, it was risky, but it had the shape of a path forward. Banting took his idea to John McLeod, a prominent physiologist at the University of Toronto who knew the diabetes literature well. McLeod was skeptical. Many people had tried similar approaches, but he also recognized a stubborn determination in Banting and agreed to give him limited lab space and a small number of animals for an experiment. McLeod also assigned a student assistant. That student was Charles Best, young, eager, and far more experienced in the practical routines of physiology labs than Banting was. Best became essential almost immediately. He could handle animals, run assays, and manage the endless technical details that turn an idea into data. Banting brought the obsession, Best brought the hands and the steady rhythm. The work began in the summer of 1921, and the conditions were difficult in every way. The lab was hot. The experiments were messy. Dogs were operated on, their pancreatic ducts tied off. The team waited for the pancreatic tissue to degenerate. Then they removed the pancreas, ground the tissue, and prepared extracts. They induced diabetes in other dogs by removing their pancreases and watched their blood sugar rise. Then they injected the extract and measured what happened. At first, there was chaos. Animals died. Extracts were inconsistent. Measurements were tedious and imperfect. But then something happened that has the quiet thunder of real discovery. The blood sugar in diabetic dogs dropped after injection. The dogs improved. Their urine sugar decreased. Their condition stabilized. It wasn't a cure, it was a treatment. But it was the first credible evidence that they had found the missing biological key. They called the extract islatin at first, focusing on the islets as the source. Later, the substance would be named insulin, from insula, meaning island, a reference to the islets of Langerhans. The name stuck because it captured the essential truth. This was the pancreas's island signal to the rest of the body. As the results became clearer, McLeod became more involved, providing resources and legitimacy. Another crucial figure entered: James Collip, a biochemist who helped purify the extract. This was vital, because the crude extracts could be toxic. To treat humans, insulin needed to be purified and standardized. Without Collip, the leap from lab dogs to human patients might have stalled. In January 1922, insulin was given to a teenage boy named Leonard Thompson at Toronto General Hospital. He was 14, emaciated, and dying of diabetes. The first injection was not perfect. The extract was still impure and caused an allergic reaction. But with further purification, Thompson received another injection, and the effect was unmistakable. His blood sugar dropped. Ketones decreased. He improved. A dying child turned a corner. If you want to feel the historical force of that moment, imagine a ward full of children on starvation diets, weak, skeletal, their parents clinging to time. Then imagine a treatment that allows the body to use food again, that restores strength, that returns color to skin and coherence to thought. Insulin did not simply extend life, it returned life to the living. Demand exploded. Insulin had to be produced at scale. Pharmaceutical partnerships formed. Animal pancreases from slaughterhouses became raw material. Standardization, dosing, and clinical protocols developed rapidly. Within a short time, insulin went from experimental extract to a widely distributed medicine. Diabetes, once almost universally fatal for type 1 patients, became a chronic disease. But with success came conflict. Science is rarely pure, and this story carries questions about credit, patents, and profit. The Nobel Prize in Physiology or Medicine for 1923 was awarded to Banting and MacLeod. Banting was furious that Best was not included. He believed Best had earned equal recognition, and in protest he shared his prize money with Best. MacLeod, for his part, shared his prize money with Collip. The gestures were attempts to correct what the Nobel structure could not. The truth that this breakthrough was not the work of a single hero. There was also the question of ownership. The University of Toronto played a central role in controlling patents to ensure insulin could be produced widely. Banting himself was uneasy about profiting from a life-saving treatment. The guiding idea was that insulin should not become a luxury. Yet industrial production required companies, supply chains, and profit incentives. The tension between insulin as a public good and insulin as a commodity began early, and it has never fully resolved. In many parts of the world today, insulin remains expensive and access remains unequal, a painful reminder that scientific miracles do not automatically become moral victories. Still, the scientific achievement remains extraordinary. Banting and Best, with their collaborators, did not merely discover insulin. They proved that a missing biological signal could be replaced. They changed medicine's relationship to chronic disease. They helped inaugurate an era where hormones could be understood, purified, and administered. They opened the endocrine system as a landscape for intervention. So how should we remember Frederick Banting and Charles Best? We should remember them as a pair, because their breakthrough was born from partnership under pressure. Banting had the idea and the ferocity to pursue it. Best had the practical skill and endurance to make the work real. Together they endured failure, animal deaths, crude tools, and long nights of measurement until a pattern emerged that could not be ignored. We should also remember that insulin's story is not only a triumph, it is a warning. It shows how fragile the path is from discovery to justice. A drug can be real and still out of reach. A treatment can exist and still become a burden. The science solved a biological problem. The world still has to solve the moral one. What do we owe each other when the power to save a life is in our hands? If you want a final image, picture that summer lab in Toronto. Heat, dogs, glassware, imperfect instruments, and two young researchers leaning over data with exhausted eyes. Picture them watching a diabetic dog revive after injection, as if someone had restored a missing thread. And then picture Leonard Thompson, a starving boy, receiving insulin and turning back from the edge. That is what it meant to steal fire. You have been listening to Scientific Giants Who Changed the World. Today we followed Frederick Banting and Charles Best from an improvised late-night idea to a life-saving hormone, from the pancreas to the bloodstream, from fatal disease to manageable life. In our next episode, we will meet Jonas Salk, a man who confronted polio terror and then refused to patent his vaccine, forcing a question that still echoes through medicine and industry. When the cure is real, who should own it? This episode was written as a continuous story for the ear, because insulin's history is not a list of dates. It is a drama of urgency, collaboration, and consequence. The moment medicine proved it could replace a missing signal and give a future back to the dying.